Section 12.1, Goodness of Fit Test. The chemistry professor suspects that her current chemistry class does not follow her expected grade distribution. The data she compiled are displayed in the table, along with the expected counts we found above. Test the professor's suspicion using the alpha equals 0.05 level of significance. So first we will state the null and alternative hypotheses. In a goodness of fit test, the null hypothesis is always that the random variable follows the given distribution. So we will say the class follows the professor's expected grade distribution. The alternative hypothesis is always that the random variable does not follow the distribution, so we will say H1 is the class does not follow. The class does not follow the professor's expected grade distribution. Part B, what is the test statistic? Round to 3 decimal places. So the test statistic is the chi-squared knot value. This is something that we have to find on the calculator. We can do this in our lists. So we're going to go ahead and go to Stat, Edit, and in List 1 we type the observations, and in List 2 we type the expected counts. So in List 1 we have 6, 10, 20, 4, 10. And then in List 2 we have 7.5, 12.5, 15, 10, 5. Okay, now in List 3 is where we build our chi-squared contributions. It's for each set of values of the observed minus the expected squared divided by the expected, which we then add up. This is more easily done by just computing all of them in List 3 and then adding up all the values in List 3. So go to the very, very top like I did here. Press Enter. It should be blinking down here. And we put L1, the observed values, minus L2, the expected values, squared, divided by the expected values, L2. And when you press Enter, it will populate List 3 with what are called the chi-square contributions. So we now want to add these up, and this can be done quickly using the sum function in the calculator. So you don't really need to write these down or anything because they're already in the calculator. So let's quit out of our lists, and we're going to go to the sum function. So second, stat, and then go across to where it says math, and we want number 5, sum. So sum always refers to addition, and then we just tell it, okay, add up all the values in L3. And here it is. So let's write this down. It's about 11.067. So that is our chi-square knot value, our test statistic. That's important because we need that as the lower bound for our chi-square CDF, which is how we find the p-value. So the p-value is going to be equal to chi-square CDF. So we're finding the area under the chi-square curve. Lower bound 11.067, upper bound 1E99. The degrees of freedom is the number of categories minus 1. So there are 5 grading categories, A, B, C, D, F. So 5 minus 1 is 4. So we need to put this in our calculator to find the p-value. So that will be second vars to get our distributions menu. And I believe it is number 8. There it is. The lower bound is 11.067. The upper bound is 1E99, and the degrees of freedom is 4. Okay, and then we press Enter. So the p-value is right here. If I round to 3 places, it's about 0.026. Okay, part D, do you reject H0? Well, our level of significance alpha was 0.05. the p-value is less than alpha, which means yes, we do. Our results are statistically significant, which means they were unlikely to have happened if H naught were true. Therefore, we reject H naught. So our conclusion is there is sufficient evidence to conclude that the class does not follow the professor's expected grade distribution. Okay, let's try a couple more goodness of fit tests. So here's another one. According to the manufacturer of M&Ms, 12% of the peanut M&Ms in a bag should be brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. A student randomly selected a bag of peanut M&Ms. He counted the number of M&Ms that were each color and obtained the results shown in the table. Test whether peanut M&Ms follow the distribution stated above at the alpha equals 0.05 level of significance. State the conclusion. Okay, so let's start off by writing our hypotheses. So H naught will be that peanut M&Ms follow the manufacturer's stated distribution. And then, of course, H1 will be the opposite. Peanut M&Ms do not follow the manufacturer's stated distribution. Okay, and we have a little bit of work to do before we can get the p-value. So first of all, we have the observations here in the table on the frequencies of each color. We do need to add those up to find out how many M&Ms were in the bag total, which we need to find the expected counts. So in the bag total, if you add these up, you get 400. So now we can use that to find our expected counts. So according to the manufacturer, 12% of them should be brown. So we can compute the expected count by taking 0.12 and multiplying it by 400, which is 48. Okay, 15% should be yellow. So 15% of 400 is 60. 12% should be red. That would be the same as brown, so 48. 23% should be blue. 23% of 400 is 92. Orange is also 23%. 23% of 400 is also 92. And then green, it says 15%, which is the same as yellow, so also 60. So notice that the percentages themselves are not the expected counts. These percentages get multiplied by the total to find the expected counts. So now we can go ahead and start typing these into our lists. So I'm going to go back into Stat Edit, and I'm just going to type over these values here. So here are my frequencies, which are my observations, are going into L1, and then my expected counts will be typed into L2. So 53, 66, 38, 96, 88, 59. Then my expected counts go into L2, 48, 60, 48, 92, 92, 60. Okay, and now I want to find my chi-square test statistic. So let me clear out this L3, and I'm going to redefine it. So highlight L3 and press Enter. It should be blinking right here. So parentheses L1 minus L2. So observed minus expected squared divided by L2 expected. And then we'll populate list 3. So now what we want to do is add these values up. That will give us our test statistic. So let me get out of my lists, and I'm going to sum up L3. So second, stat, math. Number 5 is sum. And we're finding the sum of the values in list 3. So here's our test statistic, which I think I'll write it down just so I can reference it. Chi-square not equals about 3.569. Okay, so now when I find my p-value, I'm going to do a chi-square CDF. So second, bars, number 8. The lower bound, I just wrote that down, 3.569. The upper bound is still 1E99. The degrees of freedom. So it looks like there are 6 different colors of M&Ms. So 6 minus 1 is 5. The degrees of freedom is 5. Okay, and then we can press enter. And this gives us our p-value, which is about 0.613. So that is a pretty high p-value. It's certainly greater than alpha, which means our evidence is not strong enough to reject H0. So do not reject H0. So our conclusion will be there is not sufficient evidence. There is not sufficient evidence to conclude that peanut M&Ms do not follow the manufacturer's stated distribution. Let's try just one more example for the goodness of fit test. Make sure we can solidify this process in the calculator. Is the die loaded? A player in a craps game suspects that one of the dice being used in the game is loaded. A loaded die is one in which all the possibilities, 1 through 6, are not equally likely. The player throws the die 400 times, records the outcome after each throw, and obtains the following result. Do you think the die is loaded? Use alpha equals 0.01. So in this example, the total was already given to us. It says he threw the die 400 times. So these frequencies, I'm going to assume they add up to 400. And now let's think about the expected counts. So when you have a standard die, you assume you have an equally likely chance of getting any of the outcomes. So the number of times he should have gotten a 1 should be 1/6 times 400. Okay, well let's see what that is in the calculator. 1/6 times 400. Okay, about 66.67. And if you think about it, that's really going to be the same for all 6 outcomes. If they're all equally likely, they should all have gotten the same amount of times when the die was rolled. Okay, so before we turn to the calculator, let's go ahead and write out our hypotheses. So H0 would be that the die does follow the expected distribution, which of course would be that the outcomes are equally likely, meaning the die is fair. And then of course comes his suspicion. The outcomes are not equally likely, or you could say the die is loaded. It would be fine if you had said, the outcomes are equally likely for H0 and the outcomes are not equally likely for H1. As long as it's the same meaning, that's fine. They can be written different ways in this section. Okay, now let's go ahead and go into our lists. Stat, edit, and I'm going to go to list 1 and type in the observations that he got when he rolled the die 400 times. So he got a 1 62 times, he got a 2 76 times, he got a 3 76 times, he got a 4 62 times, a 5 57 times, and a 6 67 times. So notice that these don't match the expected counts, right? They shouldn't. This should be supportive of H1. Now for list 2, the expected counts, I think one way to make this more accurate would be to put the unrounded number. So here I'm going to put 1/6 times 400. This way it's not rounded. I actually get this full decimal. I mean, it looks like it's rounded, but if you scroll up, you'll see it goes on forever, right? So this will be a more accurate way to find the p-value. So I'm going to do this each time. Actually, a quicker way would be to just put 400 divided by 6 for each of them. 400 divided by 6. If you don't do this, it's probably okay. It's probably close enough, but I just want the most accurate p-value possible. So I'm going to put these never-ending decimals in here without rounding them. If you want to put 66.67 though, that's probably going to be pretty close. Okay, now let's redefine list 3. So I'm going to clear this off. So go to the top, highlight it, press enter. Now we're allowed to define list 3 with a formula. So it's going to be observed counts minus expected counts squared divided by expected counts. Okay, so here are my chi-squared contributions, which I need to add up. So let's get out of our list. And now we're going to get our test statistic by doing second, stat, go to math, and then number 5, the sum. We're going to sum up the values in list 3. Okay, so our chi-square not value is 4.67. I'm going to write that down. Chi-square not equals 4.67. And that will be the lower bound to our chi-square CDF. So now we're finding our p-value, second vars, number 8, chi-square CDF. The lower bound we just found, 4.67. The upper bound will always be 1e99 for this. The degrees of freedom, once again, will be 5. There were 6 outcomes for rolling a die. Paste, and then let's press enter to get the answer. This is the p-value. It's a pretty high p-value, about 0.457. So our level of significance was 0.01. This p-value is definitely greater than that level of significance, which means that our sample data is not considered statistically significant. Therefore, we do not reject H0. So our conclusion can be there is not sufficient evidence to conclude that the die is loaded.